Beth.
And I'm Beth.
Welcome to Physics with Beth and Beth.
Hello everyone, and welcome back to Physics with Beth and Beth. I'm Beth, and today we are diving right into Unit 7 of AP Physics 1, which is on simple harmonic motion. But before we dive into the weeds and start talking about all the stuff I have written on the board, I want us to take a moment and talk about the word simple harmonic motion, because that's kind of a scary term. It sounds really weird and fancy sciencey, and a lot of scientists and physicists and physics teachers like to throw it out there like it's nothing, even though it sounds like a lot. But it's not a lot, I promise. Whenever we talk about simple harmonic motion, all that means is repetitive motion. Some kind of motion that is repeating itself over and over. Like, for example, a child on a swing. If a child is swinging on a swing, then they swing up, then they swing back, and then they swing up, and then they swing back again. It's the same kind of thing whenever we talk about a pendulum. We'll be doing a lot of math with pendulums in this unit. Physicists love pendulums. So simple harmonic motion is things like that. It can also be, for example, like an object tied to a spring that is going up and down and up and down. Why did I use my left hand? Here we go. Up and down and up and down and up and down over and over and over again. Some kind of motion that is repeating itself over and over again, that continues going through these cycles of motion without changing. And also, whenever we talk about those cycles of motion, one word you might hear a lot is the word oscillation. All one oscillation means is one complete cycle of our motion. So if it was my object tied to a spring, it would be one complete time of our spring going down and then back up again. So that's one oscillation right there. Pretend I did that perfectly instead of messing up. So simple harmonic motion is repetitive motion, like a child on a swing, a pendulum going back and forth, a rocking chair going side to side, or something on a spring going up and down. Now, whenever we talk about simple harmonic motion, there are a few properties of an object's motion that we like to talk about a lot, because with these particular terms that I have written out here, we can use these three helpful little numbers to describe a lot of aspects of an object's motion. So the first term that we're going to use here is period. Whenever we talk about period, think about like periodically. So whenever we talk about periodic motion, that's kind of a lot of the same thing here. That means motion that is repeating itself. A period is how long it takes it, our object, to complete one complete cycle. So whenever we're talking about period, that is, we represent it with the capital letter T, which whenever we write this, think about like T standing for time. And what it is how much time it takes our object to complete one complete cycle. So it is the time it takes for us to do a full cycle. So if I was talking about my spring here, it would be how long it takes us to go all the way down and then all the way back. That's one period. If it was my child on a swing, it would be the time it takes them to go all the way back, then all the way back up to where they started. So one complete cycle of motion and the time it takes them to do that. If we think about the units of period, well, the units of time are seconds. The units of cycle are, well, there aren't any. We're just really counting a cycle, so that's just a number. So our units here are just seconds. So period has units of seconds because it's a measurement of how long it takes us to do something, which in this case is complete one cycle. Now there's one other way we can calculate it, but I'm going to give us a few more tools in our toolbox before we move on to that. Let's first talk about frequency. So frequency is very literally the opposite of period. We represent it with a little lowercase letter f. And just as period is the amount of time it takes us to complete one cycle, frequency is the number of cycles that we can complete in a given unit of time. So the units of it, well, cycle, again, that's just something that we count, divided by time, which has units of seconds. So our units here are 1 divided by seconds, which you will often sometimes see written as seconds to the negative 1 power. Now, if you're uncomfortable with negative exponents, I would really advise doing a little bit of extra practice with them. But for now, I'm just going to summarize this and say, anytime you have a number in a denominator of a fraction, so say I have a number in my denominator here that is raised to a positive exponent, I can rewrite that number as that number to the negative version of that exponent. So these two things are the same. If that's new to you, I would really advise doing a little bit of extra practice on the side regarding that, because negative exponents will never stop coming up as you go through your physics journey, and they also never stop being extremely useful. They actually make your life a lot easier a lot of the time by allowing you to rewrite gross fractions as just pretty little exponents. So, all that to say, our units here are 1 divided by seconds, or seconds to the negative first power. There's also another way we can talk about our units, which are hertz. So Hertz was a fancy science man who did a lot of cool science, so we named a unit after him, just like we did with newtons and joules. So Hertz is just 1 over seconds, or seconds to the negative 1. It means how many cycles do we complete in a given unit of time. And because that is quite literally the opposite of period, we can calculate it by just doing 1 divided by our period. Because, well, just as our period is time divided by cycle, well, we just need to flip that upside down to get to frequency, which means dividing 1 by that. And the inverse is also true. Just as frequency is 1 divided by period, our period is equal to 1 divided by our frequency. Or I could rewrite this just for funsies and a little practice as our period to the negative 1, or our frequency to the negative 1 power. So to get between frequency and period, you just flip them upside down. This top equation, that our period is equal to 1 divided by frequency, is on your AP Physics 1 equation sheet. This bottom one, that frequency is equal to 1 divided by period, isn't. So I want you guys to remember this, but you can also get to this equation by just flipping around this top one. These two are actually saying exactly the same thing, so if you forget one, that's perfectly fine. You've got this guy to start out with. So just solve for frequency and you get right back to where we started here. So these two properties are things that we like to talk about a lot whenever we're talking about simple harmonic motion. There is one more, and that is angular frequency. So remember how whenever we talked about angular velocity, that was like how many radians we covered in a unit of time? And like how 1 complete lap around our circle is 2 pi radians? Well, here, we're kind of doing the same thing. We're going to, instead of talking about cycles as cycles, we're going to divide 1 cycle into 2 pi little bits, 2 pi radians. So if angular frequency is how many radians we can cover in a unit of time, well, there are 2 pi radians per cycle, and then, well, our period is how much time it takes us to do a cycle. So our angular frequency, oops, and I should have written, which we represent with a little lowercase omega or a squiggly w, is just going to be equal to 2 pi radians divided by the time it takes us to complete 1 cycle, which is just our period. So it's 2 pi over period, which we can also rewrite as 2 pi times our frequency. It is going to have units of radians per second, or radians times inverse seconds, which, and radians are kind of unitless, we'll go more on that later. So this means this has units of radians per second, or just inverse seconds. Okay, so one thing I want to address though, angular frequency is not the same as angular velocity. They look very similar. We represent both with this little omega, which is really confusing, and another place that physicists did a really bad job at picking out abbreviations. But if I have a pendulum that is swinging back and forth, it's not necessarily going a complete circle every time it completes a lap, right? So I might have my little pendulum and a complete lap as it's swinging from like here to here and back up again. Maybe it's only going like 60 degrees or something as it's going back and forth on its little swing. But as it goes back and forth, that's 1 complete cycle. So we say that that 1 cycle is made up of 2 pi cycle bits or radians. So that's where this 2 pi is coming from. It's not the same as a measurement of angle. It's coming from a part of a complete cycle, which mathematically is like a circle, kind of. We'll do a lot of practice with this, but the most important thing is that you know how to calculate it, which is just that our angular frequency is equal to 2 pi divided by our period, which is the same thing as 2 pi times our frequency. Okay, Now that I've just spent a lot of time talking at you about a lot of these terms, let's actually try putting them into use. I have a quick little practice problem down here. So we have a rocking chair that completes 5 cycles in 12 seconds. What is the period, frequency, and angular frequency of the rocking chair? So first, let's talk about our period. We know that our period is equal to the time it takes us per cycle. So we have 12 seconds to complete 5 cycles. So we have 12 divided by 5. I can't do that in my head, but thankfully I have it written down. 12 divided by 5 is 2.4 seconds. And our units here are just seconds. So that is the period. It's just the time that we travel divided by the number of cycles it takes us. Gives us 2.4 seconds per 1 cycle. So that's our period of our rocking chair. What about our frequency? Well, there are a few different ways we could calculate this. We could say, well, our frequency is just equal to 1 divided by our period. We could also say it's equal to our number of cycles divided by our time. Both will give us the same answer. Goodness, that's terrible handwriting. Our frequency is equal to our cycles. We completed 5 cycles in 12 seconds. So we have 5 divided by 12, which means that our answer here is 0.4167 hertz. We'll do a little bit of rounding here, and that gives us 0.42 hertz. I could also easily say that my units here were inverse seconds. They're exactly the same thing, but we're going to give Mr. Hertz his due here and use his name for our units here. I could also have calculated this, just to be explicit, by doing 1 divided by my period, which was 2.4. So I could have just done 1 divided by 2.4, and that gives you that exact same answer. So this would have given us the exact same thing. And now, because I'm running out of room, we're going to move up here and do our angular frequency up here. So to find our angular frequency, we just do 2 pi divided by our period. So this is just 2 pi divided by our period, which was 2.4 seconds. So then, if I want to calculate my period, that's 2 pi divided by 2.4, which gives us 2.618, which is the same. We're just going to round a little bit here. This is 2.6 radians per second. We could have also calculated this as 2 pi times our frequency. So 2 pi times 0.42, which would have also given us the same answer of 2.6 radians per second. All right, now that is an introduction to simple harmonic motion. Thank you so much for sticking with me through all of that. Y'all are troopers, and happy physicsing.